So imagine that this is my new coordinate, this is my basic coordinate system. So this arrow shows the unit vector in the x2 direction, and the green arrow shows the unit vector in the x1 direction, and these lines show the magnitude of the unit vectors, right? So it's like a graph plot. So our unit vectors are same in the magnitude in x1 axis and x2 axis, and they are I and j, right? So now if we change this coordinate system to something like this, so you can see the old coordinate system behind with the not so bright lines. So if you can see this white line, that was our initial coordinate system. Now we want to work in this new coordinate system where our unit vector along x1 direction has been the same as it was in the initial coordinate system, except that the unit vector is now 3 times higher or bigger than the unit vector we had in the initial coordinate system. So in this case, this dimension of this rectangle is 3 times of the dimension of the square we had, right? So our I vector is 3 times higher than the initial I vector. What happened to our unit vector in the x2 direction, the new x2 direction, is now has a multiplier of 1 in x direction and 2. So our new x2 direction unit vector is 1i plus 2j times the old unit vector. So our new vector j, capital J for instance, is equal to 1i plus 2j of the old coordinate system. So that's how we have modified it. Now in this coordinate system, our vectors multiplier will be changing. But are there something which is not going to change? Can you see something? So any vector which was along the x1 axis of the old coordinate system is not going to change. So anything which was along this direction is not going to change. The direction. So the direction of any vector which was in x1 direction is not going to change. That is going to remain invariant, but the magnitude will be changing now. So in the new coordinate system, the magnitude will be 1 by 3 times of the what you have previously, because our basis vector is now 3 times higher, right? So apart from that, is there any other vector which is not going to change? So you may look in this direction. What happens in this direction? So if you see there, the vectors in this direction are also not going to change, except they will have a multiplier of 2. So some of the things are not going to change if you change the coordinate system from that initial one to this one, and these things are called invariants. Now this vector which is not going to change is called the eigenvector, right? And by the amount it is going to change in the magnitude is called the eigenvalues. So eigenvectors are nothing but the stretch of the initial vector. It can be a stretch or it can be a squeeze. So either the new vector can be higher or it can be smaller. It can be squeezed in the new coordinate system. So relative to what our new basic vectors are. For example, if you had a vector which was just I, 1i in the initial coordinate system, in the new coordinate system that will be 1 by 3i. So you see that vector has squeezed by in the magnitude in the new coordinate system, but in reality no, right? So the eigenvectors are the vectors which are not going to change by the change of coordinate system, and eigenvalues are the values which appear as the multiplier in these invariant vectors. So now we will see that when we define stress, our definition of stress is based on the coordinate system we choose. So any transformation on a vector when results in the same vector multiplied by a scalar, then this vector is called eigenvector, right? And the scalar multiplier is eigenvalue. So now suppose I had the vector r in the initial coordinate system, and I transformed the coordinate system, and that transformation is represented by this tensor T. Tensor T represents the transformation matrix. And so when you apply that transformation to this vector, you again get the same vector, but the magnitude changes by the scalar. So when this happens, then this r vector is an eigenvector and lambda is the eigenvalue. If the same thing happens to our traction vector, then from that traction vector, if you remember, we talked about traction vector is the vectorial form of stress. So if the same thing happens to the traction vector, we can find out the principal stresses or eigenvectors when we will have the invariant values of traction vector. So instead of talking about traction vectors, we will talk about stress now. So what will happen if I have the initial stress of sigma, and then that becomes identical to an identity matrix with a multiplier of lambda, then I will fulfill this condition. So in order to do this, so we are transforming the stress tensor such that it results in a tensor with no shear component. So if you remember, it will change in the identity matrix, which we call identity tensor, with a multiplier of lambda. So maybe some of you are confused what we are doing here and why we are doing it. So let me just try to elaborate a little more. So suppose this is a rectangular block, and you are applying stresses axially on this rectangular block. So you're applying sigma, I don't know, x. So in that case, this will be my x-axis, and the other axis is y-axis. So we are applying sigma x, and we are not applying anything in this direction. So if I take the stresses at a small box here at the center, so we are calculating stress at a point, but in order to define that point we have to make a box, because we need to know the plane on which the stresses are. So we imagine that this box is getting compressed, and it is very close to becoming a point. But in order to have a schematic, I have made this box a little bigger, right? So what is happening here is when you apply sigma x, there are no stresses in the y direction, there is no shear stress also. So there is only sigma x here. So in 2 dimension I will have the stress tensor equal to sigma x, sigma x, nothing in the shear direction, nothing in the shear direction, nothing in the other axis direction, so y-axis. So this will be my stress component, this will be my stress tensor. But what if I rotate my coordinate system? So I am not changing anything in the reality, I am changing my assessment by making an element which is not aligned with the stress application point. So my element is now this, and for this I take a coordinate system which is in this direction. Alright, so this is my x dash now, and this is y dash. So when I rotate my stress element, then I will have shear stresses. You can already imagine, because this line is not aligned in the axis of the rectangular block where the stresses are applied in the initial coordinate system. So if I rotate my stress element, my stress tensor is going to change, as I explained this for the vector. So the stress in reality is not going to change. Because of my assessment and change in coordinate system, the values of the component here will be changing. So I will have stress, shear stresses. I will have sigma y dash. So in the y dash I will have some amount of stress, and if I keep on rotating, the things will be changing. And so by trying on all the rotations, I will always reach a position where shear stresses will become zero. I can always do that with any stress tensor. I can always find a rotation where the shear stress becomes zero. So when I reach there, then I get only normal stress, and those normal stresses are the eigen values of the stresses. So we call them principal stresses, right? So in order to find principal stresses, we will have to solve this equation. So now you can understand that I had a sigma which has all shear and normal component, and I am applying a transformation on that so that I get an identity matrix. So in identity matrix, except diagonal, everything else is zero. That means I have no shear stress. So I want to know for which value of lambda I will get the situation where my shear stresses will become zero. So in order to do that, let me just erase this. Can I erase all in one? Okay. So in order to solve this equation, I will have to rewrite it in this form, and then sigma minus lambda I is equal to 0. My stress tensor is this, minus lambda into identity tensor is equal to 0. So then I substitute lambda from this, and this becomes my equation. And for this to have a solution, a non-trivial solution, it is only possible when the determinant of this will be 0. So meaning that it is invertible, so it cannot be. So the inverse of this equation does not exist. If there is an inverse, then this will not become 0. Therefore, we will have to find out the determinant of this tensor to be equal to 0, and determinant of this tensor will result in this cubic equation, a cubic equation of sigma. So I will have 3 solutions. Because we are dealing in 3 dimension, for the stress component we will have 3 solutions, and these 3 solutions will be 3 principal stresses. Now I1, I2 and I3 are the coefficients of this equation, and we already talked about some vectors which do not change, and we call them invariants, and those will be the solution of this equation. But I1, I2 and I3 are also some, so these coefficients are important because these coefficients are also invariant, and invariant means something. It gives you a signal about reality. So when something is not changing, if you are changing the coordinate system, there is something important about that, which we will see in the next slide. So in this case, you see the first coefficient is the summation of all the normal stresses, and summation of all the normal stresses will not change even if you change the coordinate system by any amount of rotation. This signifies something. So we have already seen that the sigma mean or pressure of the system or hydrostatic component of the stress tensor is described by the summation of normal stresses divided by 3. So it's an average of the normal stresses, right? So that signifies the hydrostatic component, the pressure in the system, and this pressure will never change even if you, because that is the reality. If you take an element, pressure of the system, so we are not talking about fluid pressure, we are talking about the hydrostatic stress. So the stress which works like a pressure kind of thing. So that is not going to change even if you change the element. So if you remember the square box which I made in the rectangular block, where, so this was the rectangular block and we applied stresses along this direction and that direction, and so if I have because of this axial stresses, if I have certain amount of pressure, so in this case the pressure will be just sigma x, because the average stress, there is no axial stress, so there is no sigma 2 in this direction. So my mean stress will be sigma x plus sigma y plus sigma z. Sigma z is not there, sigma y is not there, so sigma x will be my pressure. Sigma x by 3 will be my pressure. So I keep on rotating this block. So I make a stress element like this, or I make a stress element like this. The mean stress is going to influence both in the same way, right? So this property, this is not going to change whatever we do, and we will see it mathematically also in a while. And then the second coefficient is the cofactor. Yes, I think it is the cofactor when you determine determinants. So this is that, and I3 is a complicated combination, and these three are not going to change whatever you do to the stress tensor. So these three are invariant properties. The importance of principal stress is have been found in many applications. So for example, in cleavage fracture, so in a brittle fracture, so brittle fracture happens in steels which is BCC at a very low temperature, which is called nil ductility temperature. So there you will have complete brittle fracture. You can also have brittle fracture above nil ductility temperature. So in brittle fracture, the probability of fracture is defined by the zone of the stress which is made by the maximum principal stress, right? And there is a crack. So I have with hacksaw or something I have created a crack, right? And then my probability of cleavage fracture will be defined by a volume which exists just ahead of crack tip, and that volume is something like this, and the boundary of this volume is defined by so here is the volume of maximum principal stress. This is the contour of maximum principal. So in this area, if you see only the top face of this thing, then it will look like this. Sorry, the side face. So it will look like this. And this kind of circle is the boundary of maximum principal stress. So anything under this circle is above maximum principal stress. So this is the importance of maximum principal stress, and then we will also see that the difference into maximum principal and minimum principal stress is always the maximum shear stress. So we will see that. So now we know about this. Now we will try to understand what happens to stresses in 2 dimension, right? So in this picture we are interested in calculating stresses at this point. Let's call it O. So at this point, right? And in order to make our calculation simple, we imagine an oblique plane, which is this, and the area of this oblique plane is A. Okay, so area of this oblique plane is this, defined by A, and we want to know that what will happen if we change our coordinate system to the stresses in 2 dimensions. So we forget about third dimension. We imagine that there is no stress in third dimension. So now my question to you will be that can you write the 3-dimensional stress tensor for no stresses in x3 direction? So that condition we call plane stress condition. So plane stress means that the stresses are only on a plane. In the third direction we don't have any stress. So that third direction is coming out of the screen, the screen you are looking at. We don't have stresses in that direction, we only have stress in x direction and y direction, right? So initially we know what are the stresses on x direction, what are the stresses on y direction. We want to know what will happen in x dash and y dash direction when that becomes our coordinate system. What will happen then? So our stresses are sigma 2 2, which is working. So you know that the first index describes the plane, second index describes the direction. So sigma 2 2 direction will be in y direction, sigma 1 1 direction will be in x direction, and these two are normal stresses. Sigma 2 1 is the shear stress which is working in this direction, and sigma 1 2 is the shear stress which is working in this direction on this plane. Okay, so what sigma 1 2 is trying to do? Sigma 1 2 is trying to rotate this triangular thing, triangular element. So this is the element I was talking about in that rectangular block diagram. So you can make a square element, but in this case we have made a triangular element. So this shear stress sigma 1 2 is trying to rotate this triangular element counterclockwise, right? So it is trying to rotate it in counterclockwise direction, and sigma 2 1 is trying to rotate it in clockwise direction. Now because of equilibrium, because this triangular element cannot rotate, so sigma 1 2 will have to be equal to sigma 2 1, but opposite in direction. So sigma 1 2 is equal to minus sigma 2 1, the magnitude of both these stresses, and this is true in every case, that the magnitude of these two shear stresses are always same. So sigma xy is equal to sigma yx, or sigma 1 2 is equal to sigma 2 1. There is a change of direction, that's it. So now imagine that when we change our coordinate system, the new stress which appears normal to this oblique plane is sigma, and the shear stress which appears is tau, right? And this angle theta is the angle made by the normal on this oblique plane. So the component of this stress on the initial coordinate system, which is shown by the red arrow, will be what? Will be Sx will be sigma cos theta, and Sy will be, so Sx is the component of sigma in x direction, and component of sigma in y direction will be sigma sin theta. So if you do force balance in x direction, you will have Sx, which is this, into the area, but area which is in this direction. So area component in the x direction will be, you have to take the normal. So the normal of the plane defines any plane. So that will be a cos theta, right? So we will have sigma 1 1 into a cos theta, and sigma 21, which is working also in the x direction, sigma 21, and the direction is x direction, so so you don't have to multiply with the direction, but you have to multiply on the plane the stress is working. So sigma 21 is working on this plane, right? So the component of area in this direction is a sine theta, right? So that will be sigma 21 a sine theta. So then if you divide, so you take a there, so Sx becomes this. Similarly, if you do the force balance in y direction, you will get this result. Then we find the component of Sx and Sy in the x dash direction. Okay, so we are actually reverting back to the same thing what we did, but this is important. So we found the component of sigma in x and y direction, which was Sx and Sy, and now we want the component of Sx only in this direction, in the direction of x dash. So let's call that Sx dash will be this, which will be Sx cos theta, and similarly the component of Sy in x dash direction will be Sy sin theta. So we are not taking sigma y dash and sigma x y dash, because we will do that in a very simple way. So forget about y direction, y dash direction, we are doing only for x dash direction. So this will be the component of Sx in x dash direction, this will be the component of Sy in x dash direction. So therefore the normal stress on x dash direction will be this component plus this component, so Sx cos theta plus Sy sin theta. We know what is Sx from our previous equation is this, we know what is Sy, which is this, so now sigma x dash is this, right? Now you multiply this and use the trigonometrical formula of cos 2 theta and sin 2 theta. So there is a mistake here, this should be sin 2 theta. So this should be sin 2 theta. So this equation will change to this form, right? So this is our normal stress in the x dash direction. What will be the normal stress in y dash direction? That you can get simply by replacing this theta with theta plus 90, because you know that y dash direction is this direction, y dash direction is this direction. So this y dash direction is actually 90 plus theta. So when you replace this theta in this equation by theta plus 90, you get sigma y dash. Okay, so that we will do for sigma y, and the shear stress, the parallel stress in the x dash direction can be found by the component of our Sx and Sy in the parallel direction, right? So that will be Sy cos theta minus Sx sin theta. Now we know the values of Sx and Sy, and you put that and you get the shear stress again in the terms of sin 2 theta and cos 2 theta, which looks like this, right? Now remember these three equations and try to see what we can see in these three equations. So sigma x dash, sigma y dash, and tau x dash. We don't have to find out tau y dash, because tau x dash will be equal to tau y dash. So we only have one shear stress. We actually have two shear stress in mutually opposite direction, but the expression will be same. So what we already studied for 3 dimension, that I1, if you remember, the invariant one, the coefficient of this equation, if you remember, yes, this one, you know, the summation of all the normal stresses is an invariant. That you find again to be true here. So what happens is sigma x dash plus sigma y dash. These are the normal stresses on the oblique plane. If you add these two, what will happen? This will cancel out, this will cancel out, and you will have this plus this, which will be sigma 11 plus sigma 22. So this is not going to change. Then if you see when sigma 12 is equal to 0, that means when shear stress is equal, so this sigma 12, when that is equal to 0, sigma x dash and sigma y dash achieve maximum and minimum value. This you can check simply by finding the first derivative of sigma x dash and sigma y dash and putting that equal to 0. And you can see if that happens when shear stress is equal to 0. Right? And the third observation is maximum shear stress occurs between maximum and minimum values of normal stresses. This we will see a little later very clearly. So first of all, in order to find the third observation, you will have to find out the maximum value of sigma x dash, the minimum value of sigma x dash, and then you will have to find out what is where the maximum shear stress is falling. Right? You can maximize this expression to find out maximum shear stress also. So in order to have this function to have a maxima, del tau x dash by del theta has to be 0, and for that you can find out what is the value of theta. Right? You will get a value of theta with this expression, you will get a value of theta of this expression, and you will see that the difference in the theta obtained here and there will be 45 degrees. So the maximum shear stress will fall somewhere between two principal stresses. Okay. So now we do a little bit of trick with this expression, these three expressions. So what we do is when we rewrite that equation of sigma x dash, so the first term here is sigma 11 plus sigma 22 by 2. So this is sigma mean, this is the mean stress, right? So we take sigma mean on the left hand side, sigma x dash minus sigma mean is equal to, it becomes this. Now we have shear stress expression in this form. If you square these two equations and add these two, so sigma x dash minus sigma mean whole square plus tau x dash square will be equal to, and if you do the square on the right hand side of these two equations and solve those, you will find this to be true. So that you can already see, because once you make a whole square of this first equation on the right hand side, you will have sigma 11 minus sigma, so this expression whole square cos 2 theta square plus sigma 12 sine square theta plus 2 into this, right? And then you can write this to be minus sigma 11, so take the minus out of this bracket and you can write it sigma 11 minus sigma 22, right? And then square will cancel out the minus, so minus into minus is plus, so you will get the same expression. So the first expression of this equation, when you take this square, it will be same as in this equation. So you will have sigma 11 minus sigma 22 by 2 whole square, take that common. In the bracket you will have cos square 2 theta plus sine square 2 theta, so that will be 1. So that's how you get this. Then you get this, and minus 2ab and plus 2ab term will cancel out. So this, if you can calculate maximum shear stress, as I told you, by maximizing this equation, you will find that this is the expression of maximum shear stress, square of maximum shear stress. So now if I rewrite this again, so this becomes sigma x dash minus sigma mean whole square plus tau x by whole square is equal to tau max whole square, right? Now this looks like an equation of a circle if you have sigma x dash and tau x dash as the x and y axis, right? So if you have a coordinate system with sigma x dash and tau x dash as axis, then this equation represents a circle, and that circle is called Mohr's circle because it was discovered by O. Mohr. Okay, so now we want to see how that how that circle looks like. Because what is the importance if you can do something like a circle or a drawing, a schematic representation of stresses? The importance will be you will be able to find out just by measuring using a scale on the graph paper different values of stresses and principal stresses by if you rotate the stress tensor by any degree. So keep on changing the value of theta. In order to do that without Morse circle, you will have to put the values of theta in this equation, and you can simply get the values of sigma x dash, sigma y dash, and tau x dash, right? But on Morse circle you can see that and you can measure it without using these equations. Before that, we will try to see the variation of sigma x dash, sigma y dash, and tau x dash, what happens when we do that, right? So before going to Morse circle, we will try to check our observations which we talked here, right? So remember these three equations, and we will try to do that in MATLAB. We will try to plot it in MATLAB, okay? So command window, right? And now I want to plot it till 360 degrees. Okay, so I have to make the matrix or an array which represents all the angles. So let's say that theta is from 0 with an interval of 2.5 degrees till 360 degrees. Okay, and then I'll have to change this from degree to radian, so I will call it rad, which will be equal to theta into pi by 180, right? Into pi divided by 180. So this is my radian values. Now I have angle. Now I have to write the expression of sigma x dash and sigma y dash. So before that I have to fix sigma x y, sigma y, and tau x y, right? So we will call it sigma 1 1, sigma 1 1. Let's say the value of sigma 1 1 is 80, right? And sigma 2 2 is, I don't know, 20, and sigma 1 2 is equal to minus 10. Now I will find out what is the value of sigma nu, let's call it here, which is sigma x dash. So sigma nu will be, by the formula it was sigma 1 1 plus sigma 2 2 by 2, right? So 0.5 into sigma 1 1 plus sigma 2 2 divided by 2 is already done. That's done. And then sigma 1 1 minus sigma 2 2 by 2. So I can just copy this, and I just have to change the sign here. So this is that into cos 2 theta. So into cos of 2 into rad, right? That will be that, plus I have sigma 1 2 into sine 2 theta. So sine of 2 into rad. So this is my sigma nu. Let's call it sigma nu 1, because this was sigma x dash. Then I have to make sigma nu 2. Sigma nu 2 will be, if you can see the equation, we have not much of a difference. So let me copy this thing again. And so the first term was same, this second term has a negative sign, and the third term also has a negative sign. So this is my sigma y dash, and then then my shear stress on the new axis is sigma shear, let's call it sigma shear is equal to, and let me just paste that again so that I have all the expressions. So I have to write sigma 22 minus sigma 11 by 2. So by 2, this is opposite, sigma 22 minus sigma 11 by 2 into sine 2 theta, so this is sine, and plus tau xy cos 2 theta, so this is sigma 1 2 and 2, so this is cos 2 theta. So I hope all my expressions are right, and I have provided all the values. So now I have the values for the stresses in the new coordinate system, right? And let's plot one by one. So I want to plot theta not in radians but in degrees. I want to plot theta and sigma x dash, which is sigma nu 1. So sig nu 1, and I want to plot it in circles with dashed line. Okay, right, I do that, and it will take some time. Now it has plotted, so let me see how it looks like. So it looks like this. Let me just, but it's okay. Now let me just plot the other two stresses also. So I'll say I'll keep the same plot, and I will plot sigma nu 2 over that. So I will plot sigma nu 2, which will look like crosses, and then I will plot sigma nu 3, which will look like this, and I will make a triangle with a line, and I will plot that also, right? And let's see how the new figure looks like on with all the three. Oh, there was a problem in this expression, plot theta versus sigma. Oh, the shear stress was called sigma shear. So we have to write sigma shear, but before, I think, hold on, once written should work, but I will just try it again. So that should do it. So yes, so it does. So what do you see here in this plot is, what we see here in this plot is the circle is sigma x dash, and sigma x dash repeats itself after 180 degree, right? So after 180 degree, you see here it will be 180 degree. So it reaches the same value, right? And what is the maximum value of this? The maximum value of this is 80, which was our value of sigma 11. What is the minimum value? The minimum value is 20, and so we didn't have minimum value for sigma 11 because sigma 11 was just one value we provided. So one observation is that it repeats itself, right? And then this triangle is the maximum, is the shear stress. So shear stress becomes maximum halfway. You can see this? Can you see this? That this is the minimum of sigma x dash. This is the maximum of sigma x dash. So between halfway of these two values, so just don't move anywhere. So between halfway of these two values, the shear stress becomes maximum. So this curve, the triangular curve, it becomes maximum in the halfway. So this was one of the observation. What was the other observation? The other observation was that sigma x dash becomes minimum and maximum, and the difference between minimum and maximum was 90 degrees, right? So you can see that it is 90 degrees because x is 80 here, and here x is 170, right? So 170 minus 80 is 90 degrees. So that's the difference. Okay. So this we have seen. Now we will start with Mohr's circle. I think we can finish it. I think we can finish Mohr's circle at least in 2 dimensions in this lecture itself. So that was a little bit with the values, and you can play with these equations and you can plot those, and you can see what happens when you rotate the stresses by changing the angle. Where is the maxima and where is the minima? So now you know that this equation is the equation of a circle when you plot these two. And how do we plot Mohr's circle? So we define our x-axis along this direction. So x-axis is sigma dash, y-axis is tau dash, right? And now we'll have to define a convention that shear stress, which will cause a clockwise rotation, will be on the upper side, and shear stress which will cause an anti-clockwise direction will be on the lower side, right? So in order to make that circle, we first plot the point of sigma x, so sigma 1 1, and anti-clockwise shear stress. So sigma 1 1 clockwise shear stress. So sigma 1 1 sigma 2 1 and sigma 2 2 sigma 1 2. These two, and we draw a line between these two, and the midpoint will be sigma 1 1 plus sigma 2 2 by 2. So this is the center of that circle. So we have found our center, and we know that these 2 points will lie on the surface of the circle. You can check that equation of the circle. So now we can draw this circle. This is our circle, right? What happens here? What happens at this point? And what happens at this point? You know, at this point, let me just use pen. So what happens at this point and at this point is that the shear stress becomes 0, right? You can see that. So when do we have shear stress as 0? We have shear stress as 0 when we have achieved the principal stress value. So this is my principal stress value, which is equal to sigma 2. So it's just a name, sigma 2, and this is sigma 1 because sigma 1 is smaller than sigma 2. So this is my minimum principal stress. This is my maximum principal stress. Okay. The other thing which is there in Mohr's circle is this angle. So the angle between the initial stress sigma 2 2 and the principal stress sigma 2 is 2 theta. In Mohr's circle, this angle is actually double, right? Because it is because you can see here that sigma 1 1 and sigma 2 2 were orthogonal. Sigma 1 1 is applied on the x direction. Sigma 2 2 is normal on the y direction, right? So the difference between these two should be 90 degree, but you can see here that the difference is actually 180 degree. So in Mohr's circle, the angle is multiplied twice just because it is represented in that way. So using the same idea that the angle is double, you can see what is the angle between maximum principal stress and minimum principal stress. In this diagram it is 180 degree, so in reality it will be 90 degree, right? And the maximum shear stress is the radius of this circle. The magnitude is the radius of that circle, and maximum shear stress will fall between sigma 1 and sigma 2. So the radius, something like this, will be, that is my radius, and this is my maximum shear stress, right? And if you remember that equation, that this was the square of tau max, so radius is square, so the radius is maximum shear stress, and maximum shear stress will fall between sigma 2 and sigma 1, so not 90 degree, but in reality it will be 45 degrees. Okay, so this was all about Morse circle in 2 dimension. We will see in the next lecture how and what changes when we talk about stresses in 3 dimension on this circle. Okay, thank you.